So last time we were talking about tensor and Hom complexes. And I had some problems with the signs in the Hom complex. It's actually not difficult. It was just off by a single sign everywhere. And you can find the correct statement with exercises in the seminar sheet. This week on Wednesday, when the second seminar usually takes place, it was a holiday, and so there was no seminar. And so today, to allow the other seminar group to catch up, we'll have the seminar, but it'll be very informal. So I can just answer whatever questions you like. OK, so today I want to talk about projective and injective modules. And we'll have a characterization of these. You'll see why they're natural notions. But they're also going to be important for approximating modules by a complex of projective or injective modules. And this is how we will compute various invariants in homological algebra. So let me start with the motivation. In the category of R modules, it might be the category of abelian groups, if R is just the integers. If I have here some module X, and then Homming out of that module, this is a functor to abelian groups, so to Z modules. And this is right adjoint to the functor which takes a Z module. Write it like this. And tensors on the left with X, and R acts on the left. And since it's right adjoint, this functor Hom preserves limits. In particular, it preserves kernels. And we discussed in the seminar, it's not hard to check, that that means that this functor sends left exact sequences to left exact sequences. Of R modules to left exact sequences of abelian groups. But in general, it doesn't preserve exact sequences. It doesn't preserve exactness on the right. So for example, if I just to give a very specific example, consider let R just be the integers, let X be Z mod, the module Z mod n, and consider the short exact sequence like this, which is multiplication by n. I could give lots of examples. This is a very simple example. Now I hum Z mod n into here. There are no non-zero homomorphisms from Z mod n into Z, because where the generator is here has to go to something of finite order, so it has to go to 0. So Hom from Z mod n into here gives, well, 0, 0, 0, and then whatever the endomorphisms of this are. And whatever this group is non-zero, because it in particular has the identity. Okay, so this is non-zero. And so this is not surjective. And so the sequence over here, it's exact on the left for very stupid reasons. It's true in general, but here it's obvious. But here it's not surjective. So it took the short exact sequence and only sent it to a left exact sequence. Okay. Similarly, so likewise, I could consider Hom into X instead of out of X. So you can check, it's basically the same argument as we would do here. You can check that Hom into X takes right exact sequences two left exact sequences. And the reason you go from left to right is that when you hum into something, it's contravariant. It reverses the order of the arrows. So I'll spell this out. So suppose I had my right exact sequence like this. This is my right exact sequence. If I hum into it, I'll get Hom from n into X. And that will inject into. This surjection will become an injection. And then the kernel of this composite will be the image of this. But then over here, I don't necessarily get an injection. So this, I don't necessarily get a surjection. So this will be an injection. The kernel here will be the image there. But here, it's maybe not a surjection. Even if this was a short exact sequence. Okay, so let's give an example of that. This is also easy. I think basically the same example works. Yeah. So let's take the same example. Then applying Hom into Z mod n. Gives the following. So Hom from Z mod n into Z mod n, it is what it is. I don't even care. In fact, I think it identifies naturally with Z mod n, because I just have to send the generator to something of order n, and everything here has order n. And then I get homomorphisms from Z into Z mod n. And again, okay, so this is, let's see, Z mod n. This is also Z mod n. I just tell you where the generator goes. All the terms are Z mod n. However, what is this map? It was the composite of a homomorphism from Z to Z mod n with multiplication by n. So it just multiplies the homomorphism by n. So this is multiplication by n under this identification. Okay? And multiplication by n on z mod n is actually equal to 0. Okay, so this map here, n is just 0. And so the kernel is the image, which is everything. Okay? And that's obviously not surjective. Okay, so this is what happens in general. When you hom out of some module, it will preserve left exactness, but maybe it doesn't send surjections to surjections. And when you hom into something, it turns something right exact into something left exact, but it maybe doesn't send an injection to a surjection. In general, it doesn't. And so modules which have additional exactness properties are very important. So let me give a definition. So two dual definitions. So we say a module X in R mod is projective if, so what was, this will be the one where we hom out. So what was the problem with exactness? It was that I would have a surjection, but not every map into the target comes from a map to the source. Okay? So we say an R module is projective if for all surjections of modules, let's say M onto N, and all maps of R modules, let's say, so let's call this, I don't know, Q, it's a quotient, and all maps from X into N. So actually I'm going to call it P to remind you that I'm defining projective. There's a lift like this, so that if I compose, I get my map F. And I'm going to draw a diagram, because this kind of situation where you characterize objects by having lifts of certain maps with respect to other certain maps, it's a pattern that appears a lot in homotopy theory and in algebra. So let me draw it like this. I draw my surjection here. And I draw here the map 0, sorry, that's fine. I'll just give myself more room. So I draw the surjection on the right-hand side. And I'm given a map here, F, from P. I have a commutative diagram with 0 up here. And I'm asking that I can lift here. That's why it's called a lift, because you draw it vertically like this. Okay, I'm asking that this exist for all diagrams of this sort. So the way that's said is you say a module P is projective if this map 0 to P has what's called the left lifting property with respect to surjections. And that was the only thing preventing exactness for homming out of a module. And so another way to say it is the module is projective if homming out of it is always exact. So alternatively, P projective if the functor hom out of P is exact. Okay. And we'll describe more or less where projective models come from. We'll give a characterization of them. That's pretty easy. But before I do that, I want to define the dual notion. And we'll spend longer on the dual notion today because it's a little more subtle. So the dual notion is the following. We had this other situation where we hommed into something and it wasn't exact. So we'd like to know the modules for which it is. And what went wrong for homming into, the problem was that it turned surjections into injections, but it didn't turn injections into surjections. So we say a module I in our mod is injective if for all injections like this, so I'll call it I, and all maps let's say F from L to I, there's an extension of F onto an extension of I to little I to all of big I. Sorry, to all of M. There's an extension let's call it F tilde from M to I, so that restricted to L, it's the map F we started with. So okay, and let me draw that in terms of filling a diagram. Okay. So what this means is that now for all injections and all maps F from L to I, so of course this commutes. And so I'm asking for all injections, there's a lift like this, or extension. Okay? So this is saying that a module I is injective if the map from I to 0 has the, if injections have the left lifting property with respect to those. Okay. So alternatively, in terms of the Hom functor, I is injective if Hom into it is exact. Because that's saying when I Hom into it, if I want it to be surjective onto Hom from L to I, and all I have to do is extend it to a map from M to I that restricts to the given map from L to I. Okay, so these are the two dual notions. Are there any questions about these definitions, what they say? We'll give characterizations and examples in a moment. Note our example here is Z mod n. This is a non-example. It's neither projective nor injective, because homming out of it and homming into it were not exact. Okay? Okay, so here's something easy we can say about projective modules. No, I'm not lifting anything from I, and there's no surjection.
No, you mean I, you assume that I is injective, right?
Mm-hmm.
So 0 must be over L.
Why?
You must have a map from 0, L, and N.
Why?
Because
Just ignore 0 for a minute.
And then 0 is not exact.
is that exact? The map from
Just right there, ignore 0. This diagram commutes automatically because the total composites are just the 0 maps. So ignore 0. I'm just saying that any map from L to I and an injection extends to I. And that's exactly what I need so that Hom M to I be surjective onto Hom Li. Anything here comes from something here. Not uniquely, just in some way. There's some extension. It's not necessary, but the reason I did it that way is it later better matches. It better matches a pattern. So there's a kind of a notion of kind of relatively injective or relatively projective, where I have some other object here, which has this property with respect to some other class of maps. So this is just meant to be pattern matching for the future. Okay, so, but yes, there's no additional logical content to putting the 0 there right now. Okay, so lemma. A module this is projective if and only if it's a summand of a free module, possibly a very big free module. So to be very clear, I mean direct summand of a free module. And I'll spell that out. So there exists a set I and an isomorphism. Let me say it like this, and an injection, and a split injection. A split injection from X, so I can inject into a free module whose basis is indexed by I. And since it's a split injection, so what does that mean? It means that the whole free module will be X plus whatever the kernel is of the retraction. Okay, so that's the sense in which it's a summand. And this is actually easy to prove. It's kind of deceptively easy because it turns out for interesting rings, free modules can have lots of interesting summands. But for very special rings, I mean, for instance, for the integers or the polynomial ring in one variable, all of the summands are actually free. So that's true for principal ideal domains. Okay, so let's see. So proof. So one direction's easy. Suppose it's a summand. Actually, both directions will be easy. Suppose X in some free module is a summand. So let's choose the complement. And let's consider a surjection. We have to test the lifting property with respect to surjections. So consider a diagram as follows. So I have a surjection from M onto N. And I'm given, that's my surjection, and I'm given a map from X. Okay. And now this sits inside X plus X prime. And I can extend it. So, and this is a free one. This is free. And I can extend it by just declaring it to be 0 on X prime. To define a map out of a coproduct, I just tell you what it does on each summand. Okay, so this will be like F plus 0. And that 0 will be on the X prime. Okay? But now, I can definitely define maps out of free things. Right, so now choose for each image, I have some basis element here. It maps to some element Ni. So for each image, choose a lift. Mi mapping to Ni. So this is from M. That's possible because Q is a surjection. This is Q of Mi. And now I'll define a map from the free module. To M lifting that. It sends EI to MI. Okay? So that, in fact, lifts the extension, and therefore lifts the map from X. This lifts this map. I don't know what to call it. F prime. And hence, by restriction, lifts the map F that we started with. Okay? So conversely, what do we have to do? Let's assume X is projective. Then we want to show that it's a summand of a free module. What can we always do for any module? We can find a free module that surjects onto it by choosing a bunch of generators for the module. For instance, we could choose as the generators all the elements of the module. That would be very redundant, but it would work. Okay? So then choose a set of generators. Let's call them like xi's of generators. And once we do that, we get a surjection from the free module onto X, which sends the free generator indexed by I to the chosen generator xi and x. But I assumed X is projective. So I can, in fact, lift the identity map. Okay, and that must be an injection because when I compose, I get the identity. Okay, so now use X projective to lift the identity map, and so split this surjection. Okay, so there you go. This can always be done. Not necessarily in any preferred way. There could be lots of choices of generators. So in some very nice contexts, there are kind of preferred ways to choose generators. And there are even algorithms for doing it in some cases. So that's how computer algebra packages work. If you have a computer algebra package that computes something about modules, or sheaves of modules, then it's because for some class of modules it knows how to find such a split surjection. Pardon? The lift will be injective because if you compose it with the quotient, it's the identity. So there could have been no kernel. So any more questions about that? No? Okay, very good. Very good. Okay, so now we want to do something similar. We have a characterization of projective modules as those which are summands of free modules. There's a characterization of injective modules, but it's a little more involved. And somehow less explicit. But we'll be able to use it in some examples, and we'll be able to use it to show that just like here, well, let me make a corollary of this, or an observation. So note in particular that free modules are always projective. So free modules are always projective. I just have to tell you where the basis elements go. I lift them along a surjection. So free modules are always projective. And every module is surjected onto by a free module, therefore by a projective module. Every module is a quotient of, is surjected onto by a projective module a fortiori a free module. So eventually we'll see projective modules that are not free, but we need to look at more complicated rings to see what they look like. Where did my chalk go? Okay, so we want some kind of characterization now of injective modules. And for this, we need a criterion. So there's, a priori, we should check if a module is injective by seeing if all inclusions extend. But it turns out to be enough to check extensions from a very special collection of injections. So this is called Bayer's criterion for injectivity. So it says a module let's say X in R mod is injective if and only if all injections of the form so there'll be some I inside R. I'll call it J because I was using I for a injective module. Right, so what is a submodule of R? It's an ideal, say a left ideal. J a left ideal, because I'm working with left modules. I could also do everything for right modules, nothing changes. So if all injections of the form, if for all injections of this form, and maps from J to X, there's an extension of F to all of R. So the lemma is saying, if I want to check something's injective, a priori I have to check this extension property for all injections, but in fact it's enough to check it for a very special class of injections given by ideals sitting in the ring. And the proof kind of both of these proofs are not really constructive because here I had to choose a set of generators. So somehow I'm using, in general, for very big modules, I'm using axiom of choice. Here, I'm not going to use axiom of choice. I'm going to use Zorn's lemma, which is equivalent. So the idea is to look at, let's see. So one direction is easy. Let me say that. So if X is injective, then we have the extension property for all inclusions. In particular for these. Okay, so conversely, suppose I know just that it has the extension property with respect to ideals. So suppose X has the extension property, map extension property. With respect to ideals, left ideals. I don't care if they are kind of ideals on both sides. And now consider a general injection. And a map from the source to X. And we want to try to extend that to all of M. And so what we're going to do is look at kind of partial extensions. We're going to look at all intermediate modules together with extensions of them. So consider, so fix, let's say fix a general injection. And now consider all pairs L prime F prime, where L prime is some intermediate module like this, and F prime extends F. In particular, in there is L comma F, the original L together with the original F. And I claim that this collection is partially ordered in a pretty obvious way. So the set of such pairs is partially ordered by the following. So L prime F prime is less than or equal to L double prime F double prime if L prime is contained in L double prime, and if F double prime extends F prime. Okay. And what we want to do is claim that there's going to be a maximal element in this partial order, and then argue that this maximal element is actually M itself. I mean on the module. And so the fact that it was maximal with extensions means there will be an extension to all of M. So how do I show the existence of maximal elements in a partially ordered set? There's a criterion for this called Zorn's lemma. So by Zorn's lemma, if all chains in this partially ordered set have upper bounds, then there's some maximal element. So let's look at a chain, and I claim it has an upper bound. And verification of that will be, it's kind of the standard thing you always do when you use Zorn's lemma with modules. You take a union. So given a chain, so it's going to be L1, F1, L2, F2, and so on. So L1 is contained in L2, F2 extends F1, and so on. So given a chain like this, let L prime be the union of all these Li's, and F prime, I'm going to write it kind of as the union of Fi's, but what I mean is, since one extends the other, if I have an element of this union, I can define the map f prime on it by just finding some Li that contains that and applying Fi. If I choose a different I, I would get the same value because one map extends the other. The restrictions are the same. Okay? So then, this is obviously an upper bound because it contains all the Li's together with an extension. Okay. So this is clearly an upper bound. Okay. So f prime of L is defined to be Fi of L for any I such that L is in Li, and that's well defined since it's a chain. Since if, let's say, like Li is contained in Lj, and this is where my L is, so it's in Li, but it's also in Lj, then if I try to compute it using Fj instead of Fi, nothing will change because one is the restriction of the other, by definition of these relation. Okay, so upper bounds exist, hence maximal element exists. And now the claim is going to be that this max, the underlying module, L prime, oh, I shouldn't have erased that. Sorry. Okay. Right, so now the claim is that this max that we found the max must be all of M. Well, together with an extension. So to see that, so indeed, suppose we have an injection which is maximal, which can't be extended any further. Or just suppose we have an extension. Let me say it like that. Suppose, I have an injection. So maybe I now call the maximal element L prime. And this is my F prime. And this is my X. And I'm trying to see this. It's maximal. So the only way, so let's suppose, let me say it like this. Suppose M is some element of big M. Okay, and consider, so I I actually want to call this L, this is just any injection. Suppose M is in here and consider an intermediate module generated by L and M. Then I claim that will always extend, F will always extend to L prime. I claim that F always extends to L prime. Therefore, if the original L was not equal to M, well, I could extend it and extend it and extend it until eventually I get every element of M. So if the maximal one was missing some element M, I could always add on M and get something even bigger than the maximal. Okay? So the maximal extension must equal M. So I need to justify this claim. Okay, so why is this? This is where we're going to use ideals in the ring. We haven't used them yet. So indeed, consider, I need to construct for you an ideal that depends on this data of the choice of little m. So consider the ideal J, which is going to be all R in the ring, such that R times this element M lands in L. So L was the fixed submodule. Then, by hypothesis on X, what do we have? Well, we assumed it had the extension property with respect to inclusions of ideals. I had the given injection, for which I'm trying to study the extension property. I have my X, like this. This was given, and I'm trying to construct this, right? Well, what do I have? Yes, so I have the map here, which is multiplication on M. And similarly here, J was defined to be all those things such that when I multiply on M, I get an element of L. Okay? And by hypothesis, I can extend the map from R into X, because X is assumed to have this right lifting property with respect to inclusions of ideals. Okay. So there exists this map by hypothesis on X. Okay. And so what does that mean? Let's see. Let's give it a name. Let 1, it's multiplication on X. So 1 goes to X. So then what? Then I claim, let's try to define. Let's try to define a map out of here. We know what we want it to do on L. There should be F. And we know what we want it to do on M. 1 should go to M, which should go to X. So then define F prime of an element here. So every element here is of the form L, something in L plus something of the form a ring element times this new generator. So I want to define this as f of L, that's given, plus R times M how do I want to say it? I think that's fine. Yeah, R times X, because I want M to go to X. And I need to check that this is well defined. If it's well defined, that's our lift, right? Because if for instance, R equals 0, then I just have an element of L, and it gives the correct value on an element L. So this will be a lift if it's well defined. An extension. This is an extension if well defined. And I claim it is well defined. Let me try to remember why. I didn't think about this for the last few hours. Okay, so why? What if I had something in the intersection? I'm kind of pretending that these things are kind of disjoint from each other. What if I had something which was both in L and of the form R times M? So indeed, to check that it's well defined, if I have something of the form R times M in L, then I get to compute this value in two ways. One way is to apply f to it. But f is R linear, so that's R times f of M. No, I don't get to do that, sorry. I don't get to do that because M is not an element of L. So what can I say? I can take R here, multiply it on M, and then apply f. Yes? Or I can include it into here, and then apply this arrow, and that will be R times X. Okay, so this equals R times X from this commutative diagram. So this was X, this is multiplication on M, this is F, and this is the inclusion. Okay, so it is well defined. So this is Bayer's criterion. And this is probably the cleverest argument we've seen so far. So I think the first one or two times I saw this, I always forget it and had to rethink it each time. Okay. So are there any questions about this? What's that? Small x is just some element of big X. It's some modular element. Any map from R to any other module is multiplication on the element. That element is wherever the unit goes to. So if I have an R module X, how do I define an R module homomorphism? From R to X, I have to tell you that 1 goes to some element, yeah? And then a general element of R will just go, R is R times 1. And so if this is R linear, this must go to R times X. Okay. So let's now let's use this Bayer's criterion. It's actually useful for checking that some modules are injective. So let's do an example, 2 examples. And we'll get to use the snake lemma now. I mean, we could do this by hand, but it would be fun to use the snake lemma anyway. Yes? The criterion is it's the summand of a free module. Is there some small class of surjections for which you could check? Maybe. I'd have to think about it. It might be something like surjections from free modules onto other modules. I'm not sure. I have to think about it. But in practice, it turns out to be easier to check that some module is projective than to check that it's injective, and this criterion is good enough. Okay, so example. So this will be in abelian groups, or Z modules. So the claim let me actually make this a lemma. It's an important fact. It works more generally than this, but this is good enough. So lemma. Inside Z modules abelian groups. An abelian group is injective if and only if for all integers, the multiplication by n map, that's always a homomorphism from the group to itself, is surjective. And so such groups are called divisible. So A is called divisible because if you look at this backwards, it's saying given an element here, I can divide it by n to find that it's in the image here. Maybe not uniquely, but there's some way to divide it by n. So if it's unique, then it's called uniquely divisible. Okay, and this is an easy, this follows easily from Bayer's criterion. Which is I test, so if A is injective, let's do the two directions. If A is injective, then it has the extension property with respect to n times z inside z. It has extension property for maps out of here. So the image of that is the ideal generated by n. That's an injection. All right, so let me write that out. Multiplication by n. Given a map here, what is it? It's just choosing an element, and then any other integer m goes to m times that element, or that element summed together m times. Okay. So there does exist an extension. Let's call it A prime. By hypothesis, A is injective. So for all A, there exists an A prime such that A equals n times A prime. And so multiplication by n is surjective on A if it's injective, if A is an injective module. Conversely, suppose A is divisible, or this map is surjective for all n. then I want to check it has the lifting property with respect to these. So let's see, how do I do this? So then consider the following again. So consider this injection, multiplication by n. Fix A. Okay, and I need to extend. And I can choose any A prime, which maps to A, and that will be an extension. So any A prime such that n A prime equals A will give an extension. Okay. So that follows easily from Bayer's criterion. And what makes that easy is that we know exactly what are all the ideals in the integers. They're just generated by some other integer n. So this kind of argument would work more generally for principal ideal domains. What was special about the integers here is that we knew all of its ideals were generated by single elements. Okay. So that's a lemma. And now let's give examples of divisible abelian groups, therefore injective abelian groups. So claim is that Q is divisible. Indeed, if I have an element of the form P over Q, then I can write it as P over n times Q times n for any non-zero n. So I guess I should have said that, right? I should have said here, for all n non-zero. Of course, if A is a non-zero group and n is 0, then it's not surjective. Okay, so Q is divisible. I claim also that Q mod Z is divisible. So you could check this by hand, just by using how you compute with cosets in a group. But for fun, let's use the snake lemma. So let's consider the following. So we need to see multiplication by any non-zero n as surjective. Yes? So consider the following. Let's consider the inclusion of Z into Q. That's a short exact sequence. And consider it a second time. So we have two short exact sequences. They're actually the same. And now, in the vertical direction, let's consider multiplication by n. Okay, so that's a commutative diagram. If I multiply by n and then include, I can include and then multiply by n. Same with the quotient. Okay, so this is the situation from the snake lemma where I have one short exact sequence mapping to another. It's actually a special version of it. In the most general form, I don't necessarily have an injection on this side. I don't necessarily have an surjection here. And so the snake lemma will say we'll have some long exact sequence involving kernel of this, kernel of this, kernel of this. And then the snake will go to co-kernel of this, co-kernel of this, co-kernel of that. So by the snake lemma, we get an exact sequence So here, there's no kernel, right? For multiplication by n here and here. So I'll have 0, 0, 0. So this will be a kernel here and here. And then I'll have whatever the kernel of this is. It's something. So it's kernel of n restricted to Q mod z. That does have a kernel. And then the snake lemma, this is my connecting map, will give me co-kernel of n here, which is z mod n. Co-kernel of here, which is 0, because multiplication by n on Q is surjective. And then co-kernel of this, which is what I'm trying to understand. So this is multiplication by n on Q mod z. And then, because this was surjective on the right-hand side, we actually know from the special form of the snake lemma that it's also surjective here on the right-hand side. So this whole thing is exact. And since it's exact, the kernel here, which is everything, must be the image here, which is 0. So you can check that by hand, but it's nice to use the snake lemma. So these are two basic examples of injective abelian groups, or divisible abelian groups. And this Q mod z is, in some sense, the most important of all injective abelian groups, and even the most important of all injective modules. So we'll more or less build all other examples from it. There might be others, but these are kind of the only ones that we can understand, the ones built from Q mod z. Okay, so we have 5 minutes, so let me end with what's special about Q mod z, and then we'll talk about the more general case of how to construct injective R modules next time. So, so lemma. So you remember with projective modules, with modules, I said every module was a quotient of a projective module, was surjected onto it, because in fact it was surjected onto by a free module. The dual statement is going to be that every module over R includes into some injective module. And we prove this by first proving the corresponding statement for abelian groups and then bootstrapping from there. So given an abelian group A, so a Z module, let I of A, this is going to be a product of the groups Q mod Z, and a product over what? It's a product of over all homomorphisms from A to Q mod Z. Okay, so I claim two things. So then I of A is injective. This is actually easy. The product of injective modules is injective because they're characterized by a property of mapping in, and we know how to map into products. So then I of A is injective. And the map, there's a natural map from A to I of A, which sends an element A to, so in here, I have tuples. I have elements from Q mod Z. How do I get a tuple? indexed by maps, I just evaluate those maps on A. Okay. So this is a map, and this map is injective. So every abelian group includes into an injective abelian group, a very natural one. Ah, yes, thank you. And moreover, we see from this, since this is, I claim an injection, that hom of abelian groups from A into Q mod Z, this is 0 if and only if A equals 0. Because if there are no such maps, then this product is empty. So it'll give you the 0 group here. And then A would be including into the 0 group. Okay, so proof. So I claim first I of A is obviously injective. Since it's a product of injectives, so you can easily check that injectives are closed under products. Similarly, projectives are closed under sums. And now we need to see that this is injective. So to see A to 1 over 2 I of A is injective, we must find for each element A, we must find some map from A to Q mod Z, which is non-zero on that element A. We need to show that for all A in A non-zero, there is a map from A into Q mod Z with f of A non-zero. And here, this is where we have to use Q mod Z as injective. So indeed, consider the following. So consider the map from the integers to A, which sends the generator to the element A. Okay. Yes, this is what I want to say. And then I want to define a map here. And there are only two constraints, basically. So every element here has finite order. Ah, yes. OK, so here's the point. I need this to be an injection in order to extend. So if A is of infinite, so there are two cases. So this is case 1. This is A is of infinite order, and this is an injection. If A is of finite order, it won't be an injection. But if it is, then I can just send 1 to anywhere. It doesn't matter where. Anything non-zero. I send it to some P of Q non-zero. I get an extension by some F, since the target is injective. And then F of A equals this P of Q, which is non-zero. Okay. The second case is this element A that I started with is of finite order. if, all right, so I could have, for instance, I could have chosen anything, right? So I could have chosen, for instance, 1/2. That's non-zero in Q mod Z, to be explicit. If A, so second case is if A has, in big A has order K, then we have an injection from Z mod K into A, which sends the generator 1 to A. And then I need to define a non-zero map here. And here I could just let 1 go to, for instance, 1 over K. And then there's an extension, which sends f of A to 1 over K. Okay? So in either case, whether A is a finite or infinite order, there's always some map from A to Q mod Z, which is non-zero on A, so long as A itself is non-zero. I should probably have said that. Yes, I did, for all A non-zero. Okay? So that's the proof. And we'll use this. I'll actually probably make this an exercise, how to bootstrap from this case to the general case of a module. But maybe we'll do that in the seminar next week. And I'll state it at the beginning of the lecture next week. So we'll stop now. We'll have the seminar as usual, but it will be more informal this week.